Good morning, children. Today we'll be covering interstitial voids in the chapter solids. So if you see a three-dimensional structure, the upper layer atoms, which are shown here as green colored spheres, they consist two types of voids. One voids which have one atom at the layer below and three atoms above. This kind of void, which is being surrounded by four spheres, is called tetrahedral void. And the other void is octahedral void. It is surrounded by three spheres in the upper layer and three spheres in the lower layer. 6 spheres. This void, it was left unoccupied in the previous layer and it is still unoccupied in this layer. So this empty space is being surrounded by 6 spheres, so it is called an octahedral void. So we will be covering the radius ratio for a tetrahedral void to that of the sphere and the radius ratio for an octahedral void to that of a sphere in this video. So what we are saying here is that there are two types of voids, tetrahedral voids and octahedral void. We will define them as the vacant space between four spheres having a tetrahedral arrangement is called tetrahedral void, and the vacant space between 6 spheres, which is formed by the void formed by two equilateral triangles with apices in the opposite direction. It is called a octahedral void. The void is formed by two equilateral triangles, one having apex in the lower downward direction, other having apex in the upward direction. It's a octahedral void. Now the relation of number of tetrahedral voids to the number of atoms per unit cell is that for every atom per unit cell there are two tetrahedral voids, whereas for every atom per unit cell there is only one octahedral void. So in a closed packed structure of n spheres, there will be 2 into n tetrahedral voids and n octahedral voids, and in totality there will be 3 voids, 2 tetrahedral and 1 octahedral void. Next is, let us find the radius ratio for an octahedral void. The radius ratio of radius of an octahedral void to that of the sphere. So as we were saying that an octahedral void has 6 spheres, 4 of them are shown here in this diagram, whereas the one below and one above the void are not shown. Now this small yellow colored circle, this signifies the octahedral void, and these pink colored big circles signify the atoms in which this void is present. In an octahedral void, how to calculate the radius ratio? Let us suppose that the radius of this sphere is capital R and radius of this void is small r, and the length of this unit cell is a centimeters. So let the length of unit cell be a. So in this right angled triangle you see that AC square is equal to AB square plus BC square. Now AB is A edge length, so AC square will be A square plus A square, so AC square will be 2A square and AC will be under root 2A. Then this AB is A. If we divide AC with AB, what the relation that we have is under root 2A upon, this is A. So AC upon AB will be under root 2A upon A. A cancels out, so AC upon AB is under root 2. This was in terms of A. We found out the ratio. Now we will again calculate AC upon AB in terms of radius. So you know that AB is equal to 2R, 2 big R, 2 into capital R, and AC is equal to R plus small 2R plus R. So this makes 2 big R and 2 small r's. So AC is equal to R plus 2R plus R, 2R, 2 big R's, capital R's plus 2 small r's. Taking 2 common, we can get R plus R. So AC was 2R plus 2 small r upon AB was 2R, and this ratio we have already found out as under root 2 upon 1. Taking 2 common in the numerator as well as in the denominator and cancelling them out, what is left is capital R plus small r upon capital R is equal to under root 2. Now R upon R will be 1. So 1 plus small r upon R is equal to under root 2, and small r upon R, taking 1 to this side, it will be under root 2 minus 1. Now value of under root 2 is 1.414. So 1.414 minus 1 will be 0.414. So R upon R is equal to 0.414, or small r is equal to 0.414 capital R. Thus for an atom to occupy an octahedral void, its radius must be 0.414 times the radius of the sphere. This is for octahedral void. Now to find out the ratio of radius of a tetrahedral void to that of a sphere, let us consider the diagram for a tetrahedral void. To show a tetrahedral void, we can assume that in the unit cell the spheres are present at the alternate corners of the unit cell. Here one corner, one is left, other corner, one is left, other corner, one is left, other corner. So out of 8 corners, 4 alternate corners have spheres, and the center of this unit cell will be having the tetrahedral void. Then to find out the ratio, let us again assume that the radius of the sphere is capital R, radius of tetrahedral void is small r, and this is the edge length of the unit cell, small a. So in the diagram, A in triangle, right angle triangle ABC, AC square will be AB square plus BC square. So AC will be A square plus A square is equal to under root 2A. Now the spheres A and C at the face diagonal are actually touching each other. So AC is also equal to 2 capital R. So we have AC is equal to under root 2A. We also have AC is equal to 2 capital R. So we comparing these two, we get 2 capital R is equal to under root 2A, or capital R is equal to under root 2A upon 2. Then this let this statement be taken as A, small a. Then we also find out, we have found out the value of R. Now we will find out the value of capital R plus small r. For that, let us consider this triangle ACD. AD square will be AC square plus CD square. AC square is 2A square. CD square is A square. So AD square will be 2A square plus A square is equal to 3A square. And AD will be under root of 3A square, which is under root 3A. Now tetrahedral void is present at the center of this body diagonal, so that half of AD or AD upon 2 is equal to capital R plus small r. So we get capital R plus small r is equal to AD upon 2, but AD is root 3A. So under root 3a upon 2. So we got r plus r. We also got capital R. So dividing r plus r with capital R, we get r plus r upon r is equal to root 3a upon 2 divided by root 2a upon 2. Solving this, we get r plus r upon r is equal to root 3 upon root 2. R upon r is 1, so 1 plus r upon r is equal to root 3 upon 2. R upon r is equal to root 3 upon root 2 minus 1. We're putting the values, under root 3 is 1.732, under root 2 is 1.414. This multiplies with this, so 1.732 minus 1.414 upon 1.414 comes out to be 0.225. This is the radius ratio for a tetrahedral void. And taking r to this side, we get small r is equal to 0.225 capital R. For an atom to occupy a tetrahedral void, its radius must be 0.225 times the radius of a sphere. So in any numerical, if the radius ratio comes out to be 0.225, then the arrangement must be tetrahedral arrangement. If it comes out to be 0.414, then arrangement must be an octahedral void.